Welcome to Biostatistics for Healthcare Students. In this series, we will learn statistics in a simple, practical, and beginner-friendly way for research, proposals, and manuscripts in healthcare and allied healthcare sciences. Let us begin with one honest point. Many students feel worried when they hear the word biostatistics. Some feel confused, some feel blank, and some immediately think of difficult formulas and calculations. If you feel like that, you're not alone. This first video is here to help you overcome fear and get started the right way. Biostatistics often feels difficult, not because students are weak, but because it is often taught in a disconnected way. Students are given terms before meaning, formulas before understanding, and test names before they even know what question they are trying to answer. That is why many learners start memorizing words like p-value, standard deviation, chi-square, or ANOVA without understanding where these ideas actually fit. And when learning starts like that, the subject naturally feels heavy and stressful. Now let us replace one wrong idea with one correct idea. Biostatistics is not just mathematics. Yes, numbers and calculations are part of it, but the real purpose of biostatistics is much more practical. It helps you understand data, answer research questions, compare groups, and make evidence-based decisions. In simple words, biostatistics helps you move from numbers to meaning. Once you see it like that, the subject becomes much easier to approach. So, how should you learn biostatistics properly? Start with the research question. Then understand the type of data. Then understand what kind of answer you are looking for. Only after that should you move to the formula or the statistical test. That is the correct order. For example, in a clinical study, you may want to compare pain scores before and after physiotherapy. In a non-clinical study, you may want to examine screen time and sleep quality in students. In both cases, statistics becomes easier when you first understand the question and the data. So remember this simple line. Biostatistics feels difficult when taught without context. When it is connected to real questions, real data, and real interpretation, it becomes much easier to learn. If this format is right, I'll continue with video 2 in the same locked structure. Welcome back to Biostatistics for Healthcare Students. In the previous video, we understood that statistics becomes easier when it is connected to real questions and real data. Now we move to one of the most important foundation topics in the whole series: variables, data types, and measurement scales. If this topic becomes clear, many later things become much easier, including descriptive statistics, choosing the right test, and reading research papers properly. Let us begin with one simple question. What is a variable? A variable is anything that can change from one person to another, from one group to another, or from one time point to another. For example, age can vary, blood pressure can vary, stress scores can vary, and hand hygiene compliance can also vary. So a variable is simply something that changes, and that is why variables are the basic building blocks of research data. Now let us move to data types. At a basic level, data can be understood in two major forms: categorical and numerical. Categorical data means names, labels, or groups such as blood, group, or department. Numerical data means numbers that represent quantity such as age, weight, blood pressure, or hours of screen time. This difference is very important because the type of data influences how we summarize and analyze it. Now let us go one step deeper into measurement scales. Nominal means names only. Ordinal means order matters. Interval means equal gaps but no true zero. Ratio means equal gaps with a true zero. For example, blood group is nominal, pain severity is ordinal, temperature in Celsius is interval, and weight in kilograms is ratio. Once you understand variables, data types, and scales properly, later statistical choices become much easier. In the next video, we will move to descriptive statistics like mean, median, mode, standard deviation, and percentages. Welcome back to Biostatistics for healthcare students. In the previous video, we understood variables, data types, and measurement scales. Now we move to another very important foundation topic, descriptive statistics. Before we compare groups or test hypotheses, we first need to understand how to describe data properly. That is where descriptive statistics help us. It helps us summarize data in a simple, meaningful, and readable way. Descriptive statistics help us answer simple but important questions. What is the typical value in this data set? How much variation is present? How are the values distributed? And how can we present the results clearly? Instead of looking at a long list of raw numbers, descriptive statistics gives us a summary. It helps us understand the center and spread of the data. That is why descriptive statistics is usually the first step in analysis. Now, let us look at the main descriptive measures. Mean is the average value. Median is the middle value when the data is arranged in order. Mode is the most common value. Standard deviation or SD tells us how spread out the values are around the mean. And a percentage tells us how much out of 100. These measures help us describe data from different angles. Some tell us where the center is, and some tell us how much variation is present. Let us connect this to real examples. In a clinical study, you may report the average pain score of patients after treatment. That is a descriptive summary. In a non-clinical study, you may report the percentage of students who demonstrated good hand hygiene compliance after training. If the data is nicely balanced, the mean may be useful. If the data is skewed, the median may be more meaningful. If you are describing categories, percentages are often very helpful. So remember this simple idea. Descriptive statistics do not test big research claims. It helps us describe data clearly before deeper analysis begins. In the next video, we will move to a new topic, what a hypothesis really means in research. Welcome back to Biostatistics for healthcare students. In the previous video, we learned how descriptive statistics help us summarize data clearly. Now we move to another very important research concept, the hypothesis. Many students hear the word hypothesis very early in research, but often they only memorize a definition and do not really understand its purpose. In this video, we will make that idea simple and practical. A hypothesis is a clear and testable statement about what you think may be true in your study. It usually predicts a possible relationship, association, or difference. In simple words, A hypothesis is not just a guess. It is a research expectation that can be checked using data. That is why a good hypothesis must be specific enough to test, not vague or decorative. Let us look at two simple examples. In a clinical study, you may say, physiotherapy reduces pain scores in patients. In a non-clinical study, you might say, hand hygiene training improves compliance among students. These are hypotheses because they express something that can be tested using data. So, the hypothesis gives direction to the study. It tells us what kind of answer we are trying to examine. Why does the hypothesis matter so much? Because it gives direction to the study. It helps you focus the research question, identify key variables, and later choose appropriate analytical methods. A good hypothesis connects the question to the data. That is why vague statements are not useful. A hypothesis should be clear enough to test and meaningful enough to guide the study. In the next video, we will move on to p-values, significance, and confidence intervals made simple. Welcome back to Biostatistics for Healthcare students. In the previous video, we understood what a hypothesis really means in research. Now we move to one of the most discussed and most misunderstood topics in biostatistics: p-value, statistical significance, and confidence interval. Many students hear these words often, but they are not always explained simply. In this video, we will understand the basic meaning of these terms without fear. Let us start with the p-value. A p-value helps us judge how unusual our observed result is if there is really no effect or no difference in the population. In simple words, it helps us ask this question: if nothing real is happening, how likely is it that we would still get a result like this just by chance? A small p-value suggests that the result would be less likely by chance alone. That is why the p-value is often used when we test hypotheses. Now, let us talk about statistical significance. Very often, students are told that if the p-value is less than 0.05, the result is statistically significant. That is a common working rule, but it should not be misunderstood. Statistical significance does not automatically mean that the result is large, clinically important, or useful in real life. It only means that the observed result may be less likely to have occurred by chance alone, given the test's assumptions. Now let us add a confidence interval. A confidence interval gives us a likely range for the true value in the population. Instead of giving a single number, it shows a range, which helps us understand the precision of the estimate. For example, in a clinical study, the effect of a treatment may be shown as a range. In a non-clinical study, the improvement in student scores may also be shown as a range. So remember this simple idea. P-value helps us think about chance. Statistical significance gives a decision rule. A confidence interval gives a range and helps us judge precision. In the next video, we will move to an important warning concept. Correlation does not mean causation. Welcome back to Biostatistics for Healthcare students. In the previous video, we learned about p-value, significance, and confidence interval. Now we move to a very important thinking concept in research. Correlation does not mean causation. This is one of the most common mistakes students make while reading or discussing research findings. So, In this video, let us make this idea very clear and practical. Let us begin with correlation. Correlation means that two variables change together in some pattern. For example, as one variable increases, another may also increase, or one may decrease while the other increases. That indicates an association between them. But association is not the same as proof of cause. A correlation can tell us that two things are related, but it cannot by itself prove that one caused the other. Let us look at two examples. In a non-clinical study, you may find that students with more screen time tend to have poorer sleep quality. In a clinical study, you may find that people with higher BMI tend to have higher blood pressure. These findings may show a correlation. But from correlation alone, we cannot say with confidence that one variable directly caused the other. There may be other explanations, including hidden factors, reverse causation, or multiple influences occurring simultaneously. So why is this idea so important? In research writing and discussion, students often overstate what their data actually show. If your study only shows correlation, you should report it as an association, not as proof of causation. There may be confounding factors. The direction may be unclear, or both variables may be influenced by a third factor. That is why careful wording matters so much in research papers. So remember this line clearly. Correlation can suggest a relationship, but it does not prove cause. In the next video, we will move to how to choose the right statistical test. Welcome back to Biostatistics for healthcare students. In the previous video, we learned that correlation does not mean causation. Now we move to one of the most practical questions students ask in research. How do I choose the right statistical test? This is where many learners feel stuck because there are many test names which can seem confusing at first. But the good news is this. Choosing the right test becomes much easier when you follow the correct logic. The first step is not to open the software. The first step is to think clearly. Start with 3 questions. What is your research question? Are you trying to compare groups, look for associations, describe the data, or test for change? What type of data do you have? Is it numerical or categorical? And how many groups or variables are involved? These 3 questions already narrow your choices a lot. Now, let us look at the basic logic. If you want to compare the means of 2 groups, a t-test may be suitable. If you want to examine the association between categories, the chi-square may be used. If you want to compare means across 3 or more groups, ANOVA may be considered. If you want to check the relationship between 2 numerical variables, correlation may be appropriate. These are not random names to memorize. They are tools matched to the type of question and type of data. Let us connect this to 2 simple examples. In a clinical study, you may want to compare the pain score after 2 different treatments. That may lead you toward a test for comparing means. In a non-clinical study, you may want to compare hand hygiene categories between male and female students. That may lead you toward a test for categorical association. So remember this simple rule. Do not choose a statistical test by guessing or by copying from another paper. Choose it by linking the research question, the data type, and the number of groups or variables. In the next video, we will make this even more practical by explaining the t-test, chi-square test, ANOVA, and correlation in a simple way. Welcome back to Biostatistics for healthcare students. In the previous video, we learned how to choose the right statistical test using simple logic. Now we will make that idea even more practical by understanding 4 very common tests: t-test, chi-square, ANOVA, and correlation. These names often sound heavy at first, but when you connect them to the right type of question, they become much easier to remember. So in this video, let us keep the focus on meaning, not memorization. Let us begin with the t-test and ANOVA. A t-test is usually used to compare the means of 2 groups. For example, you may want to compare the pain score between patients receiving treatment A and treatment B. ANOVA is similar in concept, but it is used to compare the means of 3 or more groups. For example, you may want to compare the mean pain score across 3 different treatment groups. So the core difference is simple. A t-test usually compares 2 means. ANOVA usually compares 3 or more means. Now, let us look at chi-square and correlation. Chi-square is commonly used to examine the association between categorical variables. For example, you may want to see whether the hand hygiene category is associated with gender among students. Correlation is commonly used when you want to examine the relationship between 2 numerical variables. For example, you may want to study the relationship between BMI and blood pressure. So again, the idea is not to memorize names blindly. The idea is to match the test to the data and the question. Let us end with one quick guide that you can remember. If you want to compare 2 means, think about the t-test. If you want to compare 3 or more means, think about ANOVA. If you want to examine the association between categories, think about the chi-square. If you want to study the relationship between 2 numerical variables, think about correlation. This is a basic beginner level map that helps you stop feeling lost. Later you will learn that there are conditions and assumptions behind these tests. But for now, the most important thing is to link the test name to the question type. In the next video, we will move to another very practical topic: parametric and non-parametric tests made simple. Welcome back to Biostatistics for healthcare students. In the previous video, we understood the t-test, chi-square test, ANOVA, and correlation in a simple way. Now we move to another very practical topic that students often hear but do not always understand clearly: parametric and non-parametric tests. These terms may sound technical at first, but the core idea is simple. There are 2 broad approaches used depending on the nature of the data. Let us begin with parametric tests. Parametric tests are usually used with numerical data and often work best when the data meets certain assumptions, such as approximate normality. These tests commonly involve values such as means and standard deviations. Examples include the t-test and ANOVA. So when data behaves in a more regular and assumption-friendly way, parametric tests are often chosen. Now, let us look at non-parametric tests. Non-parametric tests are often useful when the data are skewed, ranked, or ordinal, or when normality assumptions are not met. These tests are helpful when the data does not behave in the smooth way expected for many parametric methods. Examples include the Mann-Whitney U test the Wilcoxon test, and the Kruskal-Wallis test. So non-parametric tests are often practical alternatives when the nature of the data calls for a different approach. Let us make this practical with simple examples. In a clinical study, hospital stay duration may be highly skewed. In that kind of situation, a non-parametric approach may be more suitable. In a non-clinical study, satisfaction may be recorded as ranks such as poor, fair, good, and excellent. That also often points toward non-parametric thinking. But if you have reasonably normal numerical data and the assumptions are met, a parametric test may be appropriate. So remember this basic rule. Do not choose between parametric and non-parametric tests by habit. Choose based on the type of data, the distribution, and the assumptions. In the next video, we will move to sample size calculation for healthcare students. Welcome back to Biostatistics for healthcare students. In the previous video, we understood parametric and non-parametric tests in a simple way. Now we move on to a topic that many students find intimidating even before they begin their studies: sample size. The good news is this. At the beginner level, sample size should first be understood as a conceptual idea, not as a formula to fear. In this video, we will make that thinking simple and practical. Why does sample size matter so much? If the sample is too small, the study may miss a real effect or produce weak, unstable evidence. If the sample is too large, time, effort, and resources may be wasted unnecessarily. So the aim is not to collect the largest possible sample. The aim is to collect a sample appropriate to the research question, design, and analysis plan. That is why the sample size is really part of research planning. Now let us ask the real question. What affects sample size? Several things matter. The study objective matters. Are you estimating a prevalence, comparing groups, or testing an association? The expected effect or difference matters. Smaller expected differences often require larger sample sizes. Variability in the data matters. More variation may require more participants. Confidence level and statistical power also matter. And in real studies, dropout allowance must also be considered. So the sample size does not come from a single magic number. It comes from planned reasoning. Let us connect this to simple examples. In a clinical study, you may want to compare blood pressure before and after an intervention. In that case, the sample size depends on the expected change, the variability, and the design. In a non-clinical study, you may want to estimate the prevalence of stress among students. In that case, the sample size depends on the expected prevalence and the desired precision. So remember this clearly. Sample size is not just a number to fill into a form. It is a planning decision related to the study's aim. In the next video, we will move to another very practical topic: what AI gets wrong in statistics planning. Welcome back to Biostatistics for healthcare students. In the previous video, we understood sample size as a planning concept. Now we move to a very practical and modern topic: what AI gets wrong in statistics planning. AI tools can be helpful, fast, and convenient, but they can also sound confident when the statistical thinking is weak, incomplete, or mismatched to the actual study. So, in this video, let us learn to use AI carefully rather than trusting it blindly. What kinds of mistakes does AI commonly make in statistics planning? Sometimes it suggests the wrong statistical test because it does not fully understand the data type, number of groups, or study design. Sometimes it gives generic sample size advice without sufficient detail on effect, size, prevalence, variability, or dropout. Sometimes it ignores important design issues like paired data, repeated measures, or ordinal scales. And sometimes it uses strong language that confuses association with causation. These mistakes can sound polished, but they are still mistakes. So, how should you use AI safely in statistics planning? First, define the research question clearly. Second, tell the AI the exact type of data you have, the number of groups, and whether the design is independent, paired, repeated, cross-sectional, or something else. Third, use AI as a helper, not as the final decision maker. And fourth, verify every important suggestion before you use it in a proposal, dissertation, manuscript, or student project. AI can assist your thinking, but it should not replace statistical reasoning. Let us connect this to two simple examples. In a clinical study, AI may suggest a test for independent groups even when the same patients are measured before and after treatment. That would be the wrong logic. In a non-clinical study, AI may provide a generic sample size for a student survey without asking about expected prevalence, precision, or dropout rates. So remember this clearly. AI is useful for support, structure, and speed. But if the input is unclear or the reasoning is weak, the output can also be wrong. Use AI after thinking, not before thinking. In the next video, we will complete this series by learning how to read statistical results in research papers. Welcome back to Biostatistics for healthcare students. In the previous video, we learned what AI can get wrong in statistics planning and how to use it carefully. Now we come to the final video of this series, how to read statistical results in research papers. Many students see results sections filled with numbers, tables, and p-values, and they feel lost. But the good news is this: you do not need to panic when you see statistics in a paper. You just need a clear reading order. When you read a results section, do not start by staring at the p-value alone. Start with the research question. What was the study trying to find out? Then identify the variables. What exactly was measured or compared? After that, look at the summary values. Are they showing mean, median, percentage, standard deviation, or something else? Then ask what statistical test was used. This order helps you understand the meaning before you judge the result. Once the meaning is clear, then look at the p-value, confidence interval, and direction of the effect. Ask simple questions. Is the result statistically significant? What range does the confidence interval show? Is the effect going in the expected direction? And most importantly, does the result have practical or clinical meaning? This last question matters a lot. A result may be statistically significant but still small, weak, or not very useful in real practice. Let us connect this to two simple examples. In a clinical paper, you may see a table showing pain scores after treatment. First, understand which groups are being compared. Then look at the mean or median, then the test, then the p-value, and if given, the confidence interval. In a non-clinical paper, you may see percentages for hand hygiene compliance after training. Again, first understand what is being measured, then what comparison is being made, and then what the numbers really mean. So remember this final line from the series. Do not read statistics as isolated numbers. Read them as answers to a research question. That is the key to reading research papers with confidence.